started because we have a lot to do today. I need to hand back all your work, okay? And I keep saying that. So what I'm going to do, I don't want to make this a distraction, you know? So if I pass it around, will you be too focused on this, do you think? There's a lot of stuff here. Okay, let me just pass this around then. There's a bunch of stuff, so just go through the whole stack, all right? And you know what? Give me half of it. Yeah, give me half of it, and I'll start it the other way. I'm collecting the quiz. If you were going to turn it in for a maximum of a 70, was it 85? And then the bonus. So I need those now. If you could turn those in, you can turn them in together and just set them up here on my desk. It was max 50. Okay, thanks for clarification on that. I did not grade the other ones because I figure I'm going to have to grade them again, all the others, so I just waited. I do have a handout. So I normally don't use color copiers because there's not one right near my office, but I tried today to use the color copier, and it spit out 8 copies and died. So I have 8 color copies, and the rest are black and white. So what I'm going to do is I'm going to give one color copy and on each table, and then y'all can fight over it. But I'll each give you. There you go. I mean, you can get to all these online, right? Oh. Okay. All right, y'all ready? All right, has everybody turned in the quiz and the bonus? Okay, so that's it. Time's up. It's at this point it's late. All right. Like I said, we have a lot to do. That may not seem like a lot. What I did was I handed you the notes for today with each example and then an entire page if you want to work the example while I'm working the example. We're moving into the next section, 8.6. I was hoping we could get this in like half a day. It's going to take the whole day, which means that we're really only going to be able to barely get into Chapter 9 by the end of the semester. We'll see some polar coordinates and stuff, but I think it's better for us to see the power series and finish it out. So we are going to now that we've looked at what a power series is and tested them for convergence, we want to look at how we can represent functions as power series. And the first thing here that I gave to you was, let's start by going back and looking at integration, trying to integrate a function like this. And as we can see below, this does not appear to be something that we can easily handle. Now, I went to Mathematica, or Wolfram Alpha, and I typed in the integral. Now, what appears on your page is, notice it's 1 over 1 plus x to the 15th. It was supposed to be 7. So I went back and did it up here so you can see it. Either way, they both are pretty bad looking, right? Imagine trying to find the antiderivative of this using integration by parts or substitution or trig sub or some technique, right? Even Wolfram Alpha it got it, but it struggled to get it, okay? So the question is, how would we ever be able to integrate something like that? Plus a constant, yeah, that's their capital C. Now go to your next page and look at the integral arctangent of x over x. And look at what Wolfram Alpha spits back at that. 1/2 I, now I is the imaginary unit, okay? Then Li, now what's Li? Li sub n of x is the Pauli logarithmic function, which you've never even looked at. And you've never even studied functions of complex variables, which means that you've got i's in here, imaginary units. So again, What are you going to do? Nothing. This reminds me, I can't go too far off on a tangent. I remember a problem that my brother posed to me back when he was in, he went to Boston University. He was an electrical engineer. And he posed this question to me. It was an integral, very difficult integral, if you try and solve it with just real numbers. But if you had studied imaginary numbers, like most mathematicians do, then it was a very simple problem. So like this problem is very easy, actually, if you understand all the imaginary stuff, but very difficult if you're stuck in real numbers, which is why Wolfram Alpha says, not even going to try it with real, I'm going to go to the imaginary functions. So we look at both of these. This is what the heck, okay? What the heck? Like, how would we even do that, right? How could we even do that? They don't look ominous, right? I mean, look at the integrals. That doesn't look that intimidating, right? It's like, okay, arctan x over, maybe there's a substitution, who knows? Well, it turns out to be impossible right now for us to do. Okay, next page. We will return to those integrals in a little while. We are going to start by talking about what we've hopefully all have burned into our brains, and that's the geometric series. One of the most important series in math, hopefully you can see that now, that we use it so often. But the geometric series is going to motivate what we do today. We know that with geometric series, that it converges if that r was less than or equal to 1 and diverges otherwise. And that if it actually converges, we actually know the sum, don't we? And it is a over 1 minus r. That was big. And you probably don't even remember when I showed you that in class. Maybe you do. When I showed you it converged to a over 1 minus r, you probably at that point didn't realize how important it was that I could find out what it converged to. But now we're going to use that. So now replace your r with x. In the geometric series, replace every r with an x and replace your a's with 1s. And you get this power series, right? This is a power series. It is the series 1 plus x squared forever. And we know that that will converge to 1 over 1 minus x, right? This is the same as a over 1 minus r. If the absolute value of x, which used to be the absolute value of r, is less than 1. And another way to write it is this way. All I did was just flipped it over and just put the 1 over 1 minus x here. And then it turns into that power series. Is that all right? I just moved the equal on the end to the front. Okay? And then in red here is what we need to kind of think about for the rest of today's class. And that is, if you ever see 1 divided by 1 minus something, that we can expand it into its power series, 1 plus u squared forever, and that will converge as long as the absolute value of what was here is less than 1. Right? All right, let's see how we can use it. Time to get dirty. I would like for us to take 1 over x plus 5, and I want us to express it as a power series. Find its interval of convergence. So what I'll do is I'll start off by rewriting it. I need to make it look like this. Somehow, I need to make it look like 1 over 1 minus u. Because if I can do that, then I can write it out as that series that we just had boxed in the previous page, right? So let me be a little clever here first. I'm going to take this right here. I'm going to factor a 5 out of the denominator so that I can get a 1, not a 5. So here we go. 1 over, let's see, 5 is going to come out. I'll be left with 1/5 x. I'll put 1/5 x and then plus 1. Do you agree with that? So now I have a 1. I have a 1. Let me switch the order of things here. My 5's still out here. How about if I do 1 plus 1/5 x? Do you all see I have 1 and 1 here matching up? Yeah? All I need is that plus there, plus 1/5 x, to become a minus u instead. So I'm just going to convert addition to subtraction by making it 1 over, here's 5, 1 minus negative 1/5 x. Do you agree? Any questions? What's u for me then? U is going to be the negative 1/5 x, right? That's my u. Now what about that 5 that I factored out? It's a constant, so I'm going to bring it all the way out in front as a 1/5. So this is going to become 1/5 times 1 over 1 minus negative 1/5 x. Any questions at all? So this right here, right, the 1 over 1 minus negative 1/5 x is going to be able to be represented as a power series. And then I'll multiply it times 1/5. So what is that power series going to be? Remember, our u is the negative 1/5 x. We can do both. Let me do it directly as the summation notation first. That should break down to be sum 1/5 times sum n equals 0 to infinity of, no, u to the n. Look at that bottom right of that box thing in the previous page. It's u to the n. I'll put it up here so you see it. Sum n equals 0 to infinity of u to the n. That up there is what I'm using. My u is here. Got it? So what is that then? Negative 1/5 to the x. Good, thank you. To the n. Now this will converge, right? This will converge if what? If, so this converges if the r, or for us the u, is less, absolute value is less than 1. So if the absolute value of negative 1/5 x is less than 1. Which is the same as, is the same as saying 1/5 times the absolute value of x is less than 1. Right? Because when I take the absolute value of the negative 1/5, it becomes positive. Keep the x in the absolute value. Keep the x in the absolute value. Now multiply both sides by 5. And then convert that into an interval. I'm not going to check endpoints, all right? Just for now, I'm not. I mean, it could be done. I'm not going to do it. Right now, that's my interval. Negative 5 to 5, maybe including 5, maybe not. We'd have to check it. But for now, that's what I've got. Okay? With me? Now, I want to express it as a power series. So let's go ahead and take this answer here, and let's actually write out some of the terms. Okay? What do you want to do with that 1/5 inside? Or outside? Leave it outside? I don't. Watch this. Bring it inside. Then break up. I'm doing this because of where we're headed, okay? We've got to be very comfortable doing things like this. I'm taking the 1/5 that's outside. I'm bringing it in. It's not raised to a power. Then I'm breaking up the negative 1/5 x to the n and breaking it up as negative 1/5 to the n and then x to the n. Now what I'm going to do is I'm going to peel a negative 1 off the negative 1/5 and bring it out as a what? Negative 1 to the n, right? And then I'll have my 1/5, and then I'll have my 1/5 to the n, and then I have my x to the n. I have 1/5 times 1/5 to the n, which becomes 1/5 to the n plus 1. x to the n. I'm doing this more because I want to show you the types of manipulations you can do with these series. We could have, at the very beginning, way up there before I did my arrow there, I could have just started plugging in values of n and then distributing a 1/5 through at the end. But getting it down to this is good to see because, you know, you go check your answer in the back of the book or later on, we're going to be trying to put series together, and so you're going to want to manipulate them first. You should get the same result either way. All right, so let's plug in 0. Let's start writing out just a few terms. If n is 0, what do you get? -1. -1 to the 0 is what? 1, and then 1/5 to the 1 was 1/5, and then x to the 0, which is 1. So I get 1/5 plus or minus. Well, but what's our next term though? When n is 1, what do you get? You get -1 to the 1, that's -1. So it's going to alternate. So this will be a minus, not a plus. So minus, and then now 1/5 to the second power, so 1/25 x to the first. Remember below these, this is with n is 0, this is when n is 1, the next one will be n is 2. Questions? I'm just plugging in values of n. So we have now, it'll be plus or minus? Plus, and 1/5 to the third, so 1 over 125, x to the second. Then minus 1 over 625, x to the third, plus ... See? Questions, comments, concerns? It converges as long as the absolute value of x is less than 5. I think somewhere on here I did this. Let me see. Which one are we doing? Oh, there it is, right there. So I'm looking right now between the interval. Let's look between the interval. There's +6 and -5. So I didn't take the time to take the vertical asymptote out of here. That red part is 1 over 5 plus x. Okay? That's what the red part is. This black represents the power series. That's only the first term, right? Didn't we get 1/5? Okay, so now what I'm going to do, 1/5 is plotted right here. You can't see it, but that's 1/5, a constant. So when I add the next term should be minus 1/25 x, right? So that created this right here, which is a line. Just has a slight slope to it now. The next one should pop in a squared, right? So you can't really see it. I'm going to back out just a little bit so you can see them a little better. Can you all see it? Start increasing the number of terms. See what's happening? So between -5 and 5, my series is starting to match up with the function. The further out I go, the closer I get. How close can I get? As close as I ever want to be. I just have to go more terms. Now, you might ask the question, what happens if you're not in that interval -5 to 5? How do we account for this part of the function then? Well, then all we do is we shift it. So instead of doing a series where we just had x, we can shift it by doing x minus a number that would move the whole series over. All right, let's get back. We have so much to do. I want to get out of this. Any questions, though? We're done? What would the answer be? Well, this technically could be an answer. This is even better. And then writing out a few terms is good too. I will specify, on a test when I say express the series, express as a power series, I will tell you if I want you to write out some terms or not. Yeah. Reconstructing. I don't know. We'll have you'll have to elaborate more on that later. Okay, let's do this. This one here is that function that we were trying to integrate earlier, right? And Wolfram Alpha had a real hard time, but it gave us something, but it was kind of ugly. Now what we're going to see is this is pretty easy to get a power series for. So I'm looking at the function, not the integral, right? Just the function. Let's just try and write that as a power series. So if I do this, I get 1 over, I already have 1 on top. I already have 1 here. I just need to change that plus to a minus. So minus negative x to the 7th, right? Be careful. This is not this, right? I mean, it may turn out to be the same thing here, but it's not. That minus x 7th is your u. The u is not negative x. Erase, damn it. All right, so everyone sees that you have your u here? That's your u. So this should turn into the power series sum n equals 0 to infinity of negative x to the 7th n, right? And this will converge if what? If the absolute value of negative x to the 7th is less than 1, which means the absolute value of x to the 7th must be less than 1. And how do you get x out of there? Out of the x to the 7th? You can take the 7th root on both sides. Essentially, that's what you're doing. It's not as simple as that, but still less than 1. That only works because it's 1 on the other side, right? So the 7th root of 1 is still 1, which gives us an interval of negative 1 to 1. Yes? Is there a root? That's a really good question. No. No, because you have to remember what the nth root meant. The nth root meant the same as raising it as 1 over x to the 1 over n. So the 0th root would mean to be trying to take 1 over 0 root. You mean raise this to the n? Then you get 1. Well, that's what we're saying. The 0th root is not defined. But that doesn't give you 0. 1 over x to the 1 over n to the n is 1 over n times n, which is 1. So x to the 1, that's just x. Yeah. I don't know if I'm answering the question or not. It's undefined. That's right. That's right. Okay. Going back to this. So we've got this, right? We know our interval of convergence. We would still have to test endpoints, but again, we're just going to let it be. And now, let me write out a few of the terms. So if n is 0, we get what? 1? If n is 1, we get negative x to the 7th. If n is 2, we get plus, right? Plus x to the 14th minus x to the 21st plus dot, dot, dot. What are some other ways I could have written this series from here? What are some other ways I could have written that? Okay, I could have gone n equals 0 to infinity, peeled off that negative and went -1 to the n. I could have gone x to the 7th to the nth. Or I'd leave it as x to the 7n. I'm just showing you some other variations of how that could look. Those are both the same. Y'all agree? Just be comfortable with any of these formats. If it's a -1 being raised to the n, you can always peel it off as a -1 to the n. Yep. All right, let's proceed. Next one. We're going to look at this and rewrite it as a power series. So far, was that okay? These first three examples are by far the easiest of what we're going to do today. So you've got to understand this, okay? Yeah, this doesn't even look close yet to this, right? That doesn't even look close to 1 over 1 minus u. But because we took Cal 2 earlier this semester, we know what partial fraction decomposition is. So we can split this into two things like this. Now, I had to get that by taking the bottom here and factoring it to be x minus 1 and 2x plus 1. I had to factor that. Then I had to use partial fraction decomposition. I'll just put P, F, D. I might need to take this phone call. Hold on. See what it is. Yes, I do. Do y'all mind? Okay, let me just make sure. It's an electrician. Hello? Oh, can you call me a little bit later? I'm sorry. At maybe 1, or can I talk with you later? Okay, thank you. I'm sorry. I'm in class. Thank you. All right, it wasn't what I thought. I'm sorry about that. I forgot to tell you I'm expecting a call. Partial fraction decomposition. Everyone all right? Okay, now each of those individually, right? Each of those individually, I should probably be able to get to look like a 1 over 1 minus u. Let me work with the first one. That one could become a 1 over, well, how about this? Is that the same thing? I just factored a negative out of the bottom and pushed it up top. Yeah. No, I partial fractioned it, though. When you partial fraction it, this is what happens. Yeah, but I already did all that. Like, I did all the work. The A turns out to be a 1, and the B turns out to be a -1. So I'm not showing any of that work. If you take the two in red over there and combine them together, get a common denominator, and put it all back, you get this. And the x plus 2 will appear up there. Is everyone okay with this step that I did? Okay, and then I have, let me see, minus 1 over 1 minus -2x. So the second one was already in that format, right? I had the 1, the 1. I just had to switch the bottom, the order, and make it a minus minus. Mm-hmm. Yeah, I'm going to just factor it out. So I'm going to go -1 times 1 over 1 minus x minus, I'll even put a 1 here just for fun, 1 over 1 minus -2x. All right, still the same thing. Now, each of these are their own power series, aren't they? So we just need to come up with the formulas for each of those. So we have the negative 1 in front. What's the power series for the yellow? So sum n equals 0 to infinity, x to the n. Does everyone understand our u is x there? And then the other problem, the u is what? Negative 2x. So I'm going to have here minus 1 times sum n equals 0 to infinity of negative 2x to the n. Now these will converge if what? Well, we have two of them now, right? So we have to check them both. So for the first one, right, for this one over here, that converges if what? Absolute value of x is less than 1, right? What about the other one? Converges if the if the absolute value of negative 2x is less than 1. What we're going to do is we're going to get two intervals of convergence, right? But your answer has to be the one that contains both. In other words, the minimum in the intersection of the two. Like if one of them, well, let's get both intervals first, and then we'll see what we get. Okay, let's see. We have this one tells us negative 1 less than x less than 1. The other one is 2 absolute value of x is less than 1, just pulling that negative 2 out. And that gives me absolute value of x is less than 1/2, which means I have negative 1/2 less than x less than 1/2. Do y'all see that? So our answer has got to be the minimum of those two, the least of the two. Because whatever x we use has to make them both converge, right? So if I pick 3/4, what would happen? If x was 3/4, this would converge, but that wouldn't. So we have to restrict it to what would work for both. So our interval of convergence is going to be negative 1/2 less than x. That's not right. Less than x less than 1/2. And of course, we'd have to check endpoints. Where would we check the endpoints? On which one of those series? Where would we test it? We would test it from the one we got it from, right? We wouldn't need to test it here. Why? Because that's included in the interval negative 1 to 1. So you wouldn't even need to worry about it. The intersection of the two sets. Minimum meaning, what do they both have in common? Minimum is a bad word to use there. I shouldn't. But when I say intersection, I don't know if that just goes over everyone's head either, you know? The intersection is more precise. Yeah, it's just a number line. Yeah, negative 1, 1. So one of our answers is everything between, right? And then here's 0. So there's 1/2, 1/2. The other answer is everything between here and here. So our final answer is the overlap, or the intersection of those two, what they have in common. The middle part. Mm-hmm. What's that? Yeah, it's kind of odd. All right, well, we are not done, okay? We are not done because what we have now is we have two power series that represent our answer. We need a single power series. So we need to combine the two together. Now, the way we're going to combine the two together can be a little bit tricky. First of all, let's take a look at the indexes on our sums. They both start at 0, right? So that's okay. You'll see that? Our indexes both start at 0. So, yes, when they're different, we have to change them. All right, that'll be one of our last examples. So right now, we can put those two together, right? We can. And since they both have negative 1s in front, how about I leave the negative 1 out just for the next step, and then I'll push it into this series in a second. I'm going to erase this number line, all right? So I'm going to leave the negative 1 out. and then I have times sum n equals 0 to infinity, and I'm going to do this in brackets, bracket. Now, what does the first series have inside of it? X to the n. What does the second series have inside of it? Negative 2x to the n. Now, I'm going to have a plus between them because I factored a negative out, right? Like I'm basically factoring a negative from both out, which makes that a plus in front. So that's going to be plus negative 2x to the n, right? Close it. Yes? A little bit more. This is negative 1 times sum n equals 0 to infinity of x to the n plus negative 2 to the n x to the n. What did I do there? I just took that negative 2 that's being multiplied in front of x, and I applied the power to both the negative 2 and the x separately. That's fair? Now, what do both of these terms have in common? X to the n, so I can factor it out. Now, I can't factor it out of the sum, but I can factor it out of the brackets. So now I'm here. Negative 1 times sum n equals 0 to infinity. Now, when I factor it out, what am I left with when I factor 1 plus negative 2 to the n, right? Then times x to the n. Still there? Now I need to take care of that negative 1 out front. Just put it back in. What would be the correct result then? Negative 1. So I'm basically multiplying the negative 1 here and to here. So let me look at this for a second. I'm doing negative 1 times negative 2 to the n, right? Can you put those together? How? How about I do this? Negative 1 times negative 1 to the n times 2 to the n. Is that the same thing? Is negative 2 to the n the same as negative 1 to the n times 2 to the n? Yes? Can you put these two together now? What is that? Negative 1 to the n plus 1, then 2 to the n. And you could even put those together if you wanted to. But you would have to add a 1 and subtract a 1. Wouldn't you? Do y'all see what I'm doing here? I mean, this is the part of this that makes it a little challenging. There's a lot of little algebra things here, properties of exponents. I'm going to try and get it all to the n plus 1. So I'm going to add and subtract a 1 from here. I'm doing that so I can do the following. Negative 1 to the n plus 1, then what? 2 to the n plus 1 times 2 to the negative 1. Damn it. Oh, shit. This is the one I was expecting, sorry. Hello? What's up? The negative, I'm distributing the what? What do you mean distributing it? Yes. No. No. Because it's multiplication right here. The question that's being asked is, does the negative 1 go to the x to the n also? And the answer is no, because that's multiplication next in between. So it's kind of like this. Let me do a quick new page for you just to show you. If I told you right now to take 3 and multiply it times 2 plus 1 times 4, what's the answer to this? It should be 3 times 3, it should be 9 times 4. It should be 36, right? It should be 36. The way you can get that is by taking the 3 and distributing it to this. Distribute that through. What would you get? You would go to the 2 and to the 1. You get 9 plus 3, right? But then you get 6 plus 3, which would be 9 times 4, which is 36, right? Or you could have done it this way. 3 times 4, 12 times 3, 36. One or the other, not both. You distribute over addition, you don't distribute over multiplication. Hold on, let me get back to where I was. Shit. How did I lose so much of where I was? Oh, here we go. What's that? The -1, because the x to the n doesn't have, the -1 is not raised to the n. Yeah. The -1 that I'm putting in is not raised to the n. If it was, then it would have never come out, but then it could join, because they have to have the same powers. Yes. Mm-hmm. Uh-huh. What about it? What? I can't do it. I don't know what n is. No. Look, don't lose sight of what I'm doing. What I'm doing is I'm showing you manipulations of series. Different ways you can manipulate series. Because this is the part of, trust me, this is the part of when you're looking at an engineering textbook and they've got a series, and all of a sudden that series says equals this, and you're like, what the hell happened? How is that equal to that? If you can't follow things like this and do them yourself, you'll never be able to see how two things are equal. So I'm just trying to show you some of the manipulations that can be done to make this thing that looked like this earlier. I'm going to take that from here and look at our final answer and look at the two of them and say they look completely different. Well, not completely, but they look a lot different, but they're the same thing. So I'm not using order of operations because I'm not trying to compute anything. Okay, let me get back to this. I put the n plus 1 on the 2 so I could put those back together as a what? -2 to the n plus 1. And then I have sitting outside of that, -2 to the n plus 1, good, times 1/2. Because 2 to the -1 is 1/2. Now that's just that second multiplication through, right? So I have what here? Plus 1/2 times -2 to the n plus 1 times x to the n. So this is what I'm talking about. You're looking at a book, you're trying to follow someone's work, and all of a sudden they go from that series up here to this series down here. You're like, what in the world happened? Remember I showed you that video about the worst horrible teacher? Remember? And he's like, oh, just divide by 1, right? And it turned out to be correct. This is the type of thing that you don't want to get hung up on later. You're like looking at a series in some class and all of a sudden it's this, and you're like, you can't do that. You have to understand how to manipulate these things. What's allowed, what's not allowed. Yeah, order of operations is only if you're trying to evaluate an expression that doesn't have variables in it, right? That everything's numbers and you just start plugging in, do this, then this, and this, and this, and this. All right, can I go on? Please excuse my dear Aunt Sally. Y'all are forcing me to check you. What's that? One? 9? 1? We're taking a vote. This is Cal 2. Since you're bringing up, please excuse my dear Aunt Sally. Okay, we're taking a vote here. You have to vote. No one can abstain from this. Okay. What? That's a division symbol. Okay. How many votes for 1 versus how many votes? What is another possibility? Maybe 9. Okay. So how many for 1? How many for 9? Okay. It's 9. Okay. Please excuse my dear Aunt Sally is one of the worst things ever taught. Because they don't tell you that multiplication, division, and addition, subtraction. They did tell you that? Yeah, most people don't get told that. So multiplication, division is not in that order. It's in the order of whatever appears first as you move from left to right. So they're equal, basically. But it's a cute little acronym thing that you can remember it, but it's incorrect. So please excuse my dear Aunt Sally. You should do, because division and multiplication appear here, you treat them equally and you move from left to right. If you have a graphing calculator and you type in 12 divided by 4 times 3, if you have one, it should spit out 9, because it knows the correct order of operations. All right. I'm sorry I had to go there. I didn't want to see that answer. I didn't want to see all those hands for 1, but that's usually what happens. It's sad. Not sad on you. It's just sad on the education system. All right. All right, we are going to move on. Let's go. We still have a lot to do. Well, you don't usually see that division symbol anymore, so that doesn't really mess you up that much, but still, just the fact that you think it's a certain way and it's not. Now, why is it that way? The only reason it's that way is because we had to agree on a way. Right? We had to say, okay, look, is it going to be division first or multiplication first? We could have said, hey, look, always do multiplication first. But we had to have a convention that we could all agree upon, or else we all get different answers. So that's the convention. And that's what a computer's programmed to do and everything else. What's that? You can go have a talk? Well. All right, here we go. Let's read through this. This is our big theorem. All right? Term-by-term differentiation and integration. Let f of x be a power series. So that's a general power series, c sub n, x minus a to the n. We have a radius convergence of greater than 0. Now that's important. Remember we said last class, 3 possibilities with power series. You could have just x equals a. In that case, the radius of convergence was 0. So if x equals a is your only point of convergence, this theorem does not apply. It's not going to happen often, but it's something to keep in mind. If you have a radius of convergence other than 0, so either an interval or everything, then f is a well-defined function. Okay, it's just like cosine or sine. It's some function. And because it's a well-defined function, we can take a derivative of it, and we can integrate it. So if we differentiate it, this is part I, we get this. And I think it's pretty easy to see. I hope it is. If I say take the derivative, where's the ruler around here? I thought there was a big old ruler in here. If we said take the derivative, here's f, right? Take derivative of this. Derivative of a constant would be 0, right? The derivative of this, well, c1 is a constant, x minus a to the first power. So the 1 would come out, right? And then it would be this to the what? 0, which means it's a 1. So you just get that constant, wouldn't you? Now, take derivative of this. 2 comes out times the constant, and then this to the first power. It's this. And then the next one, 3 comes out, squared. And you see how that works? Okay? Now, look at it this way, though. as a power series, since this down here is a power series now, I can rewrite it as a power series. So I do. Notice though, and this is huge, don't let this ever slip up on you. It's going to mess you up. When you take the derivative, you no longer start at 0 because you don't have that constant term in the front. So once you take derivative, your new power series would start at 1. And all it is the old power series. That's the old power series, right? I can't hide that, can I? But kind of, right? That's the original power series, isn't it? The only difference is we've taken the n out front, just like you do with derivatives, right? Take the n out front, subtracted 1, and increase the index by 1. So it's power rule, basically. All right, now for integration, it's the opposite. Go ahead. What? Quotient? Where's quotient? You mean product rule? Division? That is chain rule, yes. But what's the derivative of what's inside? What's the derivative of x minus a? 1. Okay, I'm glad you pointed out because maybe it wasn't obvious. The 2 comes out, or, back up here. The 2 comes out times a constant. All of this to the first power, derivative of what's inside is 1. And on each one of them, it'll be 1, 1, 1, 1, 1. So for integration, it works backwards, right? So let me look at this right here. Go back up to the original one right here. What's the antiderivative of a constant? Constant times x. Now for us, we're going to put x minus a. And does it matter that we put x minus a? Let me do it this way. The antiderivative of a constant, right, we're going to say is the constant times x minus a, instead of just saying constant times x. Is that all right? Does it matter? Distribute. What do you get? What is this? A constant, right? So with antiderivatives, don't we always have plus c? So it doesn't matter if I write it as this or a combination of the two. It's still a constant. So it doesn't mess it up to use the x minus a still, because I'm still just going to have a constant in there. I hope that makes sense. So what we have is the antiderivative of a constant is going to be the constant times x minus a. The antiderivative of x minus a would be what? So forget the c1's there, it's just a number. What's the antiderivative of x? 1/2 x squared, right? So you would basically have a c1 over 2, and then all of this squared. And then this one right here, c2 over 3, x minus a cubed, and so on and so forth. So you get this right here. It's power rule for antiderivatives. And notice that you can rewrite that in a power series, and here's the power series. What is different though? Okay, we have a constant out here, okay, which we'll just remember there's always a constant of integration, all right? Even though there's a constant in here too, we can put them together, it's still a constant. The original problem here, right, the original is that all we did was power rule, 1 over n plus 1, x to the n plus 1. That's all that happened. What about the index? Stays at 0. Because with differentiation, you kill a term off, so that's why you have to increase the index by 1. With integration, you actually don't kill off a term. You introduce a new one, actually, but you don't need to account for it. It's accounted for right here with that c. Now, other ways of saying this, other ways of representing this are written below. If you want to take the derivative with respect to x of a power series, then all I'm going to do is move the n out front. I've already said this. Move the n out front, and then subtract 1, and then change the index. If I want to take the integral of a power series, I forgot my dx out here. Then all you're going to do is power rule backwards. I mean, the power rule for antiderivative. So I add a 1 over n plus 1, and then n plus 1 up there. Remember these. I'm going to refer back to these. Let's go to the next problem. Now we tackle the problem that we had to start the class that Wolfram Alpha had a problem with, right? This one. So what we're going to do is we're going to look, first of all, at the inside. Well, we already did that problem, didn't we? Just a second ago? What did we figure out that was? It was sum n equals 0 to infinity of negative x to the 7th to the n, right? Yes? Now we want to integrate that, right? We want to take the integral with respect to x. Now before we can do this, what I need to do is take care of that alternating part. You see the alternating part, the negative? Okay. So I'm going to say integral sum n equals 0 to infinity, negative 1 to the n, x to the 7, x to the 7n dx. Now, if we look at it this way, is everyone all right with that? Okay. C sub n here is this piece, and the rest of it is like my x minus a to the n. Now, I realize it's to the 7n, but that matches up with our formula with our constant and then our x term. Yes? And according to the previous page, the integral of an infinite series, if I know what C sub n is, what happens to C sub n? Nothing. Okay? But this thing, I'm going to do 1 over n plus 1, x minus a to the n plus 1. So I'm going to divide by n plus 1 and add 1 up on the exponent. So for us, this will become equal to sum, no more integral sign, n equals what? N equals 0, right? Integration, you don't change the index. C sub n does not change. But now, times 1 over, now be careful here, n plus 1. But what's really our n? It's not n, it's what? 7n. So we're going to do 7n plus 1, x to the what? 7n plus 1 again. Questions? That's an infinite series, isn't it? Isn't that an infinite series? You want to write out a couple of terms? Yes. You don't. Yeah. Well, what will happen is that it won't affect the exponent because you still have that 7n, but the 1 divided by n plus 1 would be off. So you've got to get the x by itself. X then to whatever the power is. It's adding 1 to the power. So like when you're taking the antiderivative of x to the 9th, you always just said 9 plus 1. Good question. I know what you're alluding to. You're saying if we change the index, then you would replace n with n plus 1. That's different than adding 1 to n. All right, let's write out a few of the terms of this. What would it be? If n is 0, we get 1 and then 1 and then just x, right? Okay. Oh, I forgot something, everyone. Plus c. And we'll throw it on at the end over here too. Now let n be 1. So it'll be minus 1 over 8 x to the 8th, right? Now let n be 2 plus 1 over 15 x to the 15th minus 1 over 22 x to the 22 plus 1 over 29. I'll stop after this one. X to the 29. It would be minus next, right? Dot, dot, dot. Plus c. Do you see why they usually put the c in the very front? Because if you go dot, 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 you know, there's infinite terms and then plus c is kind of weird. So they usually put the c at the front. I don't care. Plus c is fine with me at the end. This is our answer. Or the one right above it. I'd like to do something else. Go ahead. Well, I'll get to that. Hold on. Yeah, I'll get to that. So, go back to what we did earlier. If you flip back, what did we say 1 over 1 plus x is 7 was? Not the antiderivative, but what was it? What was the actual series? Wasn't it 1 minus x to the 7th plus x to the 14th minus x to the 21st power plus x to the 28th? We could have kept going, right? Didn't we say that's what it was? What if I say now take the antiderivative of this? What do you get? What's the antiderivative of 1? Antiderivative of this? Antiderivative of this? 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 Okay? Same thing, right? So you might be saying, well, why didn't we just do it that way, right? Well, you have to be able to do it both. Because this way is easy. See, I could have easily written this out, right, to start. Said, oh, that's what 1 over 1 plus x to the 7th is, right? And then said integrate this, and we could have got this answer. But then you would have had to have turned this into a power series. So how are you going to go backwards from this to its power series? You're going to have to know what the pattern is, right? So I think it's easier to just go from the power series, use the formula, and then go to this. But you can always check your work this way, too. I don't know, did that make sense? Just look at the example we did. So with Wolfram Alpha, I will admit this. Wolfram Alpha is able to get an exact answer. Okay? Like on that front page, the very first note of this, when I did 1 over 1 plus x to the 15th, you know, I forgot I had this one up here. Here it is. This is the one for 1 over 1 plus x to the 7th. This is what Wolfram Alpha got. And I'll tell you what, I don't know if we could get this. This is an exact answer. There's a lot going on here. I mean, this would be almost torturing yourself, all right? So I don't know if we can do this, but I guarantee there are some problems that Wolfram Alpha will never get. They won't get an exact answer. Well, that's why they have a button you can click right here that says approximate form. And if you click that approximate form, they'll give you the power series most of the time. And that's what a computer scientist is going to do, and an engineer and a physicist. They're going to, a lot of times what they do is they take a function that's maybe difficult to integrate or differentiate or something, and they just convert it to a power series. And now that power series, how would you evaluate it? Like if you wanted to do an integral, go back to it right here. See our answer? How would you do something like integral, let's say 0.1 to 0.5 of 1 over 1 plus x to the 7th dx. How do you evaluate that? If I give you the definite integral, right, how would that be evaluated? Well, first you have to find the antiderivative, right? Which we did, but it's a power series. So then what you would do is you plug in 0.5 into that. Whatever that answer is, you subtract what you get when you plug in 0.1. But they're infinite, so how do you plug in 0.5? Well, you go out as far as you need to go. This again goes to, with what accuracy do you want? Do you follow that or not? It's only about, power series, we're kind of conceding the fact that we don't have the exact form, but we can get it as close as you want. No matter how tall the tolerances, no matter how tight they need to be, I can always get to that point if I need to. All it's going to cost the computer is more operation counts, a higher operation count. That's all it's going to be. And with computers, if you need me to go out 100 terms, the computer's going to do that before you could even think. It's so quick. Now, of course, you go out a billion terms, you can slow it down, but what? Oh, is the voice gone? Did I lose it? I think I just, yeah, okay, just got hidden. Thank you for letting me know. All right, well, let's proceed. Whoa. Still recording? I am recording. All right, rewrite. Can I take just a little quick step back? What we've done so far is we use the geometric series to write out series if we could get them to look like 1 over 1 minus u. That's what we've been able to do, right? And then in the last problem, we were able to integrate something that we looked at as a 1 over 1 minus u. So we turned it into its series, and then we integrated it term by term, right, each piece. And now what we do is we look at something like this. Rewrite this function as a power series. The problem with this function is that it doesn't look like 1 over 1 minus u. And there's nothing we're going to be able to do to it. No algebra is going to make it look like 1 over 1 minus u. Right? Do you agree with that? Yeah. Yes. Well, that's not even a series. That's just a function. Right? It's asking you, what is the series? What is the series that represents that function? You all understand? So this is why you're in class, so I can show you this. However, we do notice this. The derivative of f is 1 over 1 plus x, isn't it? The derivative natural log of something is 1 over. And that looks like 1 over 1 minus negative x, doesn't it? Well, it doesn't look like it is. It is 1 over 1 minus x. And that is the power series n equals 0 to infinity of negative x to the n. Yes. No. Not always. Next thing is to make sure we know when this converges. Well, when the absolute value of x is less than 1. So I'm just going to put that next to it in blue. Absolute value of x less than 1. For absolute. No. It's because remember it's r to the n, geometric. R was the thing that had to be less than or equal to.
Well, we have an example that we put x to the 7.
That's right, because it was x to the 7n. So we rewrote it as x to the 7 to the n. Yeah, what was in that parentheses there was x to the 7. Okay, are y'all okay with this? Now, I'm trying to get the power series for f of x, and all of a sudden I come in here and start talking to you about its derivative. So how are we going to get anything from this? Well, do you agree that the function itself should be the antiderivative of its own derivative? Right? So isn't it the antiderivative of the sum n equals 0 to infinity of negative x to the n? Isn't that clever? Now, I can't do the antiderivative on that yet because I've got a negative with the x. So I'm going to have to just pop that negative 1 to the n out. And that'll be my c to the n, c sub n. Integral n equals 0 to infinity, negative 1 to the n, x to the n, which is antiderivative, right? Antiderivative. So by the formula we just talked about, f of x should be equal to sum n equals 0 to infinity, right? No change on the index when I do an antiderivative. C sub n times 1 over n plus 1 x to the n plus 1. And this time it really was n plus 1 because our power was n, right? And then do what? Plus c. Which equals, let's write out a few terms. You get x minus 1/2 x squared plus 1/3 x cubed minus 1/4 x to the 4th plus dot, dot, dot. Plus a constant, right? Now you can actually determine what the constant is because all you'd have to do is come up here and plug 0 in for x. Do we all know what natural log of 1 is? 0. So when I come down here and I plug 0 in for x, I should get what? 0. That means that constant had to be 0. Because all these go away, right? 0, 0, 0, 0, 0, 0. And that constant's left, and that should be 0 then. All right. 25 minutes. We still have the big daddies to do here. All right, how about this one? Rewrite as a power series. You had to, on that previous problem, you had to recognize that if you took the derivative, you knew how to expand that as a power series, right? If you took its derivative. On this one, it's going to be even worse. All right, so we almost have the 1 over 1 minus x, don't we? Except the whole thing's cubed. So let me first rewrite it as this. X cubed over 1 minus x cubed. You cannot distribute that 3, that power, through both of those right on the bottom. Right? You cannot make that 1 minus x cubed. Please don't do that. Please excuse my dear Aunt Sally. Right? Please excuse that very bad exponent rule there. So that's what we can do so far, right? And then I can even do this, pull the x cubed off, and just write it out front like this. Does everyone agree that that's the same thing? And now it requires some pretty, I don't know. Again, something that someone showed me that I show you, right? A trick. It's not natural to see it right away first time you've ever done this. Usually you've seen it before or someone showed it to you. So watch this. I'm going to stop the problem here. I'm going to take a look at just this part right there. And I'm going to rewrite it right here. And because I was so good in calculus, I realized that that is really just the derivative of 1 over x, 1 minus x squared. Missing my 1/2, sorry. What? What I'm saying is that this right here is what you get when you take the derivative of that. Do you agree? So maybe you need to take a moment. We'll take it together, okay? Let's take a moment and look at this. This is really 1/2 1 minus x to the negative 2, isn't it? What would happen if I said take the derivative of that? Negative 2 would come out, become a negative 1 out front, times all of that to the subtract 1, negative 3, then times the derivative of what's inside, which is negative 1. So I'm doing derivative, not antiderivative, right? So that would just turn out to be 1 over 1 minus x cubed, wouldn't it? Again, not very natural to see that right away, is it? All right. But do you see it now? Okay, so do you agree with me now that this is 1/2, because I can take that constant and just pull it out. All I did was pull the constant out. Is that all right still? What happened by me noticing this? What happened? Tell me what significance, what did I achieve by seeing that? I put the power down. And what I really want is that power not to be there at all, right? Because if the power wasn't there, I've got the power series, don't I? So can I maybe see that that's the derivative again of something else? What is that the derivative of? What is that the derivative of? Do you need the half? It's 1. Let's try this. I'm hearing this. Okay, now don't forget that derivative that's out there, right? The inside of this, you're saying, and I'm hopefully agreeing with, is the derivative of what? 1 over 1 minus x. Is it negative 1? Let's check it. What is this right here? This is 1 minus x to the negative 1, isn't it? What's the derivative of that? Negative 1 comes out, right? This to the negative 2, and then times the derivative of what's inside, which is negative 1. That negative 1 hits the negative 1 that's out here and makes positive 1. So this is it. This is a little challenge, I think. I mean, even for people who are pretty quick with the derivatives and stuff, but you got to see it. What we're doing is we're working our way backwards to something that we know the power series of. So if you take the derivative of this, you get derivative of what's in here. You get this with the constant pulled out, which is just that, which is, if you take derivative of that, you get this. Questions at all? It is pretty sad, isn't it? You sure? Can I move on? Because I want everyone to be on the same page here. All right. Now what I'm going to do is this. Equals 1/2 the derivative with respect to x of, now, in here, that green derivative with respect to x of 1 over x, I'm going to rewrite that. Derivative of, now instead of writing 1 over 1 minus x, what can I write? The series, right? The series. n equals 0 to infinity of x to the n. So I'll start highlighting things. This here is this, right? It's not alternating. The green is the green, the yellow, and there's yellow. The blue is the blue. Yeah. Okay? Now, can you take the derivative of a series? We have a formula for it, don't we? What's the c sub n? 1. There's a 1 in front here, right? So what happens when you take derivative of a series? The n comes out, you subtract 1 from the n, and hold on, you're doing antiderivative. Derivative. The n comes out, n minus 1 on top. Hold on. Well, yes, derivative of x, which would be 1. But we don't have to account for that. But x minus a is 0 here. One more time. N's going to come out, subtract 1, and index changes by 1. Don't forget that step. All right, that's the critical step. Equals 1/2 derivative with respect to x. Now, I'm going to take that derivative, right? So the green's going to go away now, and I will get sum n equals 1, and I'll highlight that, to infinity of n x to the n minus 1. That's right. No, because I took the derivative. And by taking derivative, we get a new series. Now what? Well, guess what we get to do again? We get to take the derivative again. Right? C sub n is n, so just ignore it. What's going to happen is we're going to bring the power down, and we're going to subtract 1 from the power, and we're going to add 1 to the index. Again. Because that first derivative is of a constant, and that should go to 0. So you don't need to pick up that number when you start your new series. And you actually can't, because if you try to, you won't have a formula for that constant. Your formula won't work for that constant. So let's see. We have 1/2, no more derivative, right? Sum n equals 2 to infinity. So again, I am applying that rule. I have taken the derivative the second time. And now I've got, the n was already out there, right? What came down? N minus 1. Then I have x to the n minus 2, because I do n minus 1 minus 1. Beautiful. Oh no, because remember, that was just what? That was just that red 1 over 1 minus x cubed. What did I have in front of that whole thing? X cubed. So now I'm ready to come back to that. All right, I'm ready to put that one back together up there. So I'll try and squeeze it right in here. I need to do my x cubed times my 1 over 1 minus x cubed, which should be my x cubed times 1/2 sum n equals 0. Nope, not 0. Mistake. N equals what? 2 to infinity of n times n minus 1 times x to the n minus 2. You can just leave it. Yeah. Everyone see what I'm doing now? Just taking that x cubed from the very beginning of the problem, putting it back on there, tacking it onto that series. And now let's go ahead and pass the 1/2 and the x cubed through. When you do that, you get this. Sum n equals 2 to infinity n minus 1. Wait, I forgot my 1/2. Oh, I'll fix it. All over 2. How about that? and then x to the n plus 1. Good. You see what happened there? I don't like the way that looks. I'm sorry. I'm just going to fix it. N minus 1, x to the n minus 2, and then I came in with x cubed, right? Those have the same base. You add the exponents. What's x to the n minus 2 times x to the third? What's n minus 2 plus 3? N plus 1. As your brain starts to have to absorb more complicated ideas, the simpler stuff becomes stuff you forget about. Just gets shuffled away. That's it. That's the power series. You could write out some terms if you wanted to, but that's what we're looking for. I don't know about you, but that's pretty cool to me. Radius of convergence would have been 1. And we would have got that from right there. Yep. Our radius of convergence would have been 1. Because that power series, the original power series here, absolute value of x would have been less than 1. And all right, last one, 12 minutes, man. This is going to be tough. This is the hardest one today. Well, I mean, I have to build up to it. I can't just walk in and drop a nuclear bomb on you. Okay, here we go. Write as a power series. Find R and I. So forget the R and I. I mean, that's stuff we can get later. Okay, so this is very similar to the last problem, but I am going to do it this way. Watch. X cubed over 1 minus x cubed minus 2x over 1. Well, hold on a second. Now I'm thinking about this. I might want to do this a little different. Yes, that's what I'm thinking I want to do. Well, yeah, we'll do it that way. Let's see. We could do it like this. X cubed minus 2x times 1 over 1 minus x cubed, like that. Yeah, I like that. That's good. You agree with that? And all the work we just did, right? Previous page, we know what this is as a series. So this is equal to x cubed minus 2x. And then what was the 1 over 1 minus x quantity cubed? Wasn't that 1/2 sum n equals 2 to infinity of n times n minus 1 x to the n minus 2. We just did that, right? This right here was what we did in the previous exercise. I did that intentionally so we wouldn't have to work through a whole other problem just to get to that point. So there's like a good 20 minutes of work in that part right there, right? Any questions? Now what I'll do is I'll distribute. I'll take this whole thing in blue and I'll just distribute it through the parentheses. So I'll get my x cubed times my 1/2 sum n equals 2 to infinity n minus 1 x to the n minus 2 minus 2x times 1/2 sum n equals 0. Keep on doing 0. 2 to infinity n minus 1 x to the n minus 2. That was just distribution of the series, right? Yeah, I'm going to put everything back in. I'm even going to take the x cubed that's out here and put it in. I'm going to take the 2x and, well, 2 is going to cancel, but I'm going to take that x and put it back in. Do we have any questions on that, though? The reason why I'm still working with this and I'm not just like saying I'm done is because we want a power series, a single power series. Not 2 power series, 1. Maybe this one's not as bad as I thought. Okay, this will be equal to, I'm putting the 1/2 and the x cubed inside. I'll have 1/2 n minus 1 x to the n plus 1. The other one is minus, now the 2 and the 1/2 go away, sum n equals 2 to infinity, n minus 1, x to the n minus 1. Does everyone see that? That x goes in, you add 1 to the power on x. So it goes from -2 up to -1. Yeah? All right. Here's the problem that we have. Okay, we have a little bit of an issue. You have the same index right now, right? But you have your x here, x to the n plus 1 is different than that one over there, right? They're not the same. So the way we're going to do this, even though this may not make sense, is we're going to try first not to put them together, but to get the same powers first. That might seem backwards. You may say, oh, I've got the same index, let's just put these together now. If you do that, you're going to wind up having to undo it later. It's a little more work. So right now, focus your attention on the powers on x only. And what you could do to make the powers on x the same. You can make them both n plus 1s, you can make them both n minus 1s, you could change them both to n's, it doesn't matter. I suggest changing one of those to the other. And I don't care which way. Let's go with n plus 1s. Let's make them both n plus 1s. Okay? So I'm going to go for right now, I'm going to make them both n plus 1s. Now to do that, right? To do that, I'm going to have to take the one on the right, and I'm going to have to do what? Add and subtract 1? Yeah? Okay, let's go ahead and do that. Make the same, hold on. Hold on. Trying to think of how I want to language this. If we add and subtract 1, as we did before, we're still going to have the x up there, aren't we? I want to formally make sure I withdraw what I said. Add and subtract 1, right? Just scratch that. Because if we add and subtract 1, we're still going to have an x out here. We don't want that x out there. We just want that power to turn into an n plus 1. That's all we want to do. But we can't magically make it an n plus 1 unless we change the index in a way that it changes it to an n plus 1. See, there's two different things. I can either mess with the exponent by adding and subtracting things, or mess with the index and force that to become an n plus 1. So how could that become an n plus 1? If I add how much to it? 2, right? So if I change my n's into n plus 2's, wouldn't that top right one here become an n plus 2 minus 1 and become an n plus 1? Yes. I will. I will, not yet, but I'll have to do some work, but I will be able to put them together. Okay, so y'all following me? Trying to make these match. We've chosen to make them both n plus 1s, so I'm going to do an index change that will change the one on the top right to an n plus 1. which means I need to do an index change where I change all my n's over to what? N plus 2s. N minus 2. And no, hold on. Which way are we going? I'm starting to lose my own mind here. Yeah. On my work, when I did mine, I decided to change mine to n minus 1s instead of n plus 1s. But y'all want to go n plus 1 so I can throw the rest of my work away. Okay, let's do it. All right, so I'm going to change all my n's to n plus 2s. Yes? All right, let's do it. Now, it's only on this series on the right that I'm doing this. So I have minus sum. We're going to run out of time. Remember, this becomes n plus 2 equals 2 to infinity. Then I have what? All my n's become n plus 2s. N plus 2, n plus 1, x to the n plus 2 minus 1. So that's going to become n plus 1. Now my first series is still the same. I'll bring that down later. This is sum n equals what? 0 to infinity of n plus 2 times n plus 1 times x to the n plus 1. And on the left one, all right, that all right? Now we have the same powers on our x's, which means when we put them together, we'll be able to factor it out, won't we? Like we did earlier, we factor out an x to the n. Now we'll be able to factor out an x to the n plus 1. But we can't put them together unless they have the same index. So you're sitting there going, well, now we're caught in this loop, right? How are you going to get back to the index, get the indexes again? You're going to have to do this weird change of n. That's not quite true. Here's what we can do. Look at this. If I say this totally separate problem, if I say, what's the sum n equals 0 to infinity? That's 0 plus 1 plus 2 plus 3 plus 4 plus 5 forever, right? Well, couldn't I do this? Couldn't I rewrite that as 0 plus 1 plus 2 plus the sum n equals 3 to infinity of n? And isn't the first one here, these first, isn't that just the sum n equals 0 to 2 of n? And this one is n equals 3 to infinity n? In other words, what I'm doing is, if you want to go from 0 to infinity, you could, if you wanted to, first go from 0 to 2, and then add to that 3 to infinity. That's how I'm going to do this. I'm going to go back to this problem. Back to this problem right here. Can you all hang in here for another 2 or 3 minutes? What I'm going to do is, I really need them both to be at 2. All right, because the one in blue starts at 0, then goes 1, then goes 2. The other one starts at 2. So they both need to pick up at 2 together. So on the blue one, what I'm going to do is this. I'm going to go bracket sum n equals 0 to 1. Okay, 0 to 1 of n plus 2 times n plus 1 x to the n plus 1. But then plus, now the sum the rest of the way. N equals what? 2 to infinity of n plus 2, n plus 1, x to the n plus 1. That's everything in bracket, right? See how I did that? I'm kind of peeling off the first 2 terms, right? These are the first 2 terms of this series. I'm peeling them off and separating from this, well, it's the third term out. Now I can put these 2 together. I can put this and then minus this part together. Remember, I'm going to be subtracting because you see the subtraction out in front of the whole bracket? So my new sum there is sum n equals 2 to infinity of whatever was in the first one, which was 1/2 n minus 1, and then x to the n plus 1 minus n plus 2 times n plus 1, and then the x to the n plus 1. So where's my x to the n plus 1? Where is it? I factor out both. Right? The x to the n plus 1 is here, and it's here. When I put those together with subtraction, I get basically the c sub n, the thing that was in front, minus the other one c sub n, and then here's my x to the n plus 1 factored out. But what do I still have? I mean, this is done. This is that first series. What do I still have here? These two, these pieces right here. So minus the sum n equals 0 to 1 of n plus 2 times n plus 1 x to the n plus 1. How many terms is this? 2. So let's figure out what they are. Plug 0 in. What do you get? 0 in for n. 2x, right? But you're subtracting 2x. So won't I get minus 2x? And then plug in 1, what do you get? 6x squared. And you're subtracting that also. Sum n equals 2 to infinity of all this stuff. 1/2 n minus 1 minus n plus 2 times n plus 1 x to the n plus 1. This is our final answer. Sorry, I had to go over a little bit here. All right. Does it, maybe you have questions you just don't even know what to ask, but is there any of these steps that are just like completely what in the hell happened or anything? You see this peeling off here? That's pretty important, right? I feel bad because I said the wrong thing earlier when I wanted to get, you want to get these things to be the same. I did that, but you have to change the index to make them change. Yes. Yep. Radius still 1. Yep. It should be. Take what? Way back when you convert, way in the previous problem when we figured out what 1 over 1 minus x cubed was. Okay, I will, I'll tell you what your homework is now so I don't have to post it later. Oh, and you want a bonus problem, right? It's the problem I didn't get to do today. It's going to be, it's not supposed to be super challenging, okay? Yeah. Find the antiderivative of that. Remember, that's what I showed you on your second page. On your second page here of your notes, I said, how about the antiderivative of arctangent x over x? And I showed you that even Wolfram alpha spit back these imaginary valued logarithmic functions, polylogarithmic functions. Okay, you should be able to figure that out using power series. That'll be due on Tuesday. Your homework. You also want to stay and do the next section? Let's do it. All right, here's your homework. So this right here, here's your bonus, due next time. And then homework, page 474, 3, 5, 7, 9, 11, 15, 17, 25, 27, and then 36 is another bonus. Now, 36 is weird. Yeah, 36. There you go. Bonus. Have a good weekend. Do your homework. This is a hard homework section. This section is hard, all right?
Are you going to be in your office for a while?
I'm going. That's where I'm headed.